Good morning, everybody. Welcome to sunny Wednesday morning at Chem 1105 with your host, me, Dr. White. Hi, everybody. Hi, some important announcements. Let me remind you, on Monday, the 8th of this month, May 8th, I will be giving test number 4 online. By 12 p.m. or earlier, I will be sending out an email, just like I've done the other tests, with the password for test number 4 PDF file so you can open it up. You'll have until Tuesday, 1 p.m. to finish test number 4 and upload your answers for test number 4 as a single PDF file to Blackboard. Should take you about 40 minutes, but take up to 2 hours. It will cover acids, bases, organic chemistry. The test has 17 problems, 9 pages. No multiple choice questions, but some of them are multiple part, like A, B, C, and D. All right, now, test number 4 will have 56 points on acids and bases, and 49 points on organic chemistry. So there's five bonus points. Now, I reserve the right to subtract here 25. I might even do more for anybody who doesn't follow instructions, single PDF file upload, or who does not upload your answers on time. By Wednesday, 1 p.m. or earlier, hopefully by late Tuesday, I'll post the scores on Blackboard for test 4. I'll also post an announcement and send you an email for your test scores on test 4 in Blackboard. Now, on that Wednesday, after test 4, a week from today, I will go over the answers of the test number 4 in our Zoom meeting, but I will delete this from the Zoom meeting YouTube. However, I will create, like I did for the other test, a private YouTube video with the answers for test number 4 that I will send you the URL for that video. Today, I'll do a review for test number 4. Remember, next Monday, by the end of the day, is the deadline for the extra credit project if you're planning on doing it. All right, where is it? All right, here's what I was looking for. Let me remind you also, if you haven't handed in all your labs, you have until tomorrow or Thursday, the 27th. Oh, I already passed that deadline. So hopefully you got all your labs in. Don't forget to hand in the labs. Oops. All right, let me remind you again, next Monday, the 8th of May, will be test number 4. Next Monday, the 8th of May, by the end of the day, is the deadline for the extra credit project. Remember, my special offer to you is before you upload your extra credit project, if you're going to do it, remember it's optional, you can email me your extra credit project. I'll review it. Anything wrong, I'll tell you this is wrong and how I'll give you a hint how to correct it. So you should be able to get 10, yes, 10 bonus points. All right, as promised, let's go through the review for test number 4. Remember, all reviews are in the lecture section of Blackboard. let's talk about acids and bases. You should know a bronzed acid is a proton donor. Any substance that can donate a proton to another one, a proton donor. Remember, a proton is H plus. You should know what is a bronzed base. It's any substance that can accept the proton from another substance. Another way of saying that is it's a proton acceptor. Now, you should know how to identify key acids. The first one, HCl, hydrochloric acid. The second one, H2SO4, sulfuric acid. And the third one, HNO3, nitric acid. You should also know key bases, and those are NaOH, sodium hydroxide, KOH, that's potassium hydroxide, NH3, that's ammonia. Now, one I've mentioned, and you should be aware of, that's a weak base. And this is a weak base. And that's sodium bicarbonate. And you know that as baking powder. And also baking soda. Now, in water, or with water, it can react with itself with this equilibrium. And what you should know is that the ionization constant for water, Kw, named after me, I wish, is this hydronium ion concentration. When you have a bracket, that means concentration times hydroxide, and this should be 1.0 equals, let me do it correctly. Important information, test number 4 is correct. Huh. All right. Well, anyways, equals 1.0 times 10 to the minus 14. And I showed you how to use this right here to calculate the hydronium ion concentration from the hydroxide. I went over that on Monday in the problem set. Now, you should know for, oh, now it's, all right. That for aqueous solutions or acidic solution is which the hydronium ion concentration is greater than hydroxide ion concentration. For a basic solution, hydroxide ion concentration is greater than the hydronium ion concentration. And this is sometimes called alkaline. And for a neutral solution, the hydronium ion concentration is equal to the hydroxide ion concentration. Now, these are very small numbers. Because of that, it's hard to figure out this. So someone came up with a pH concept, and you should know pH is minus the log of the hydronium ion concentration. And don't tell anybody, shh, shh. But my special gift to you, if the hydronium ion concentration is 1.0 times 10 to the minus x, then pH is x. Now, let's take a second, maybe more than a second, to look at important information, test number 4. And there I give you pH equals minus the log of the hydronium ion concentration. I also give you an important information. If H3O plus concentration is 1.0 times 10 to the minus X, then the pH is X. And finally, and I'll go over more, but at not this point, Kw, named after me. No, I wish it was. But anyways, ionization constant is hydronium ion concentration times hydroxide equals 1.0 times 10 to the minus 14. And if I give you OH concentration, you can determine, which we did in a problem set on Monday, hydronium ion concentration, then use it to calculate the pH. Hold on. Sorry about that. Important phone call. All right. Now, remember the pH scale. You should use this. Now, important thing about the pH scale, you should remember, will not be an important information, and I better be subtle. Ooh, 4 explanation points. All right, you should know the pH scale. It goes from 0 to 14. At 7, you're at neutral pH. Below 7, you're at acidic pH. And above 7, you're at basic pH. And the lower it is, the more acidic, the higher it is, the more basic. Now, I just mentioned this. It's a logarithmic scale. Each number 1 is a power of 10 difference in pH. Now, speaking about pH, we mentioned some things. Your stomach contents, fluids, are acidic because there's an acid in there. Also, if you bite into a lemon or lime, it's real sour because it's acidic. There's citric acid in there. And your mother nature has given your tongue the ability to taste sour when something's mildly acidic. And you should know buffers. Buffers are a solution that resists major change. In other words, the pH doesn't change when small amounts of acid and base are added to it. And let's go back to the pH scale again. This is probably one of the most important things I'll teach you this semester. And this is probably going to be useful outside of my class that you know this in your own personal life. Remember, at 7, it's neutral pH. Below 7, it's acidic. Above 7, it's basic. Your stomach is acidic. The liquid in your stomach is acidic because there's an acid present. I guess one of the miracles for me personally about our body is we all have cells in our stomach that make hydrochloric acid, HCl, and that makes it acidic. And that, if you were taking my Chem 1212 class, organic chemistry, helps you break down food. But the real reason the pH of your stomach is less than 7 is because there's an acid present in it. And lemons and limes taste sour because there's an acid there. Now, next I talked about titration. And when you have an acid-base reaction, one color, this is called the neutralization reaction because the acid, when you add base to it, or base when you add acid to it, the pH will change and go whichever direction towards 7. When you hit 7, you're at neutralization. And at neutralization, moles of acid equal moles of base. And from this, I give you another gift. You know, for a monoprotic acid, only one proton it can give up, or monoprotic base, only one proton it can accept. This is true. Milliliters of acid times molarity of acid equals milliliters of base times molarity of base. And if you have a known amount of acid of an unknown molarity and you neutralize it, called titration, with milliliters, certain amount of milliliters of a known molarity base, you can determine the molarity of the acid, which is very important. Or if you don't know the molarity of the base, you can do the same thing, titrate the base with the acid and calculate the molarity. And I went through problems like this on Monday, last Monday. Look at the video. All right, next I got into my favorite part, organic chemistry, because Dr. White, I am an organic chemist. I'm actually a synthetic organic chemist. Synthesis is the fancy word means to make. Now, the most important thing about organic chemistry, it's based on the carbon atom. And it's based originally on things that came, molecules that came from things that were alive, plants, animals, and us. All right, now, cuddle time. When it comes to carbon, you should know there's always 4 bonds to carbon. 4, 4, 1, 2, 3, 4. 4 bonds to carbon. That's important. Know that. Because of that, carbon can bond to other elements, and most importantly, itself. And it forms long chains with or without branches and rings. Now, things you should know. Oh, I'm giving a lot of hints today. Hydrocarbons, those are molecules with only carbon and hydrogen atoms. And if you've been following the news about pollution, hydrocarbons in the air are a source of pollution that are harming our planet. And you should know a hydrocarbon is a molecule with only carbon and hydrogen atoms. Now, there are two types of hydrocarbons. One is saturated hydrocarbon, the other is unsaturated. And another hint. Wow, am I giving you a lot of hints? Now, saturated hydrocarbon, because it's a hydrocarbon, is a molecule with only carbon and hydrogen atoms, and in which all carbon-carbon bonds are single bonds. And we show a carbon-carbon single bond in organic chemistry. Organic chemists don't use Lewis structures totally. We use a line to show that's a pair of electrons being shared. Now, unsaturated hydrocarbons are molecules with only carbon and hydrogen atoms that contain one or more carbon-carbon multiple bonds, and that can be a double bond or a triple bond. Double bond, we show 2 lines, triple bond, 3 lines. Now, important part, very important part, I mean, really important part of organic chemistry are functional groups. The study of organic chemistry, especially what I am, synthetic organic chemist, deals with functional groups. And you should know how to find a functional group in a molecule. And how do you do that? Wow, somebody can count to how many hints? I think I'm going for the Guinness Book of World Records for most hints in a lecture. When you're looking for functional groups, which you should know how to do, look for anything that's not a carbon or hydrogen atom or is not a carbon-carbon single bond, because that's where the functional group is. That's where the fun is. Really, it is. That's where all the action is. Now, I will, when we go through, let's do one real quick. And the question would be, circle the functional groups in this molecule. How do you do that? Well, you look for what's different. What's not a carbon atom, hydrogen atom, or carbon-carbon single bond should get your attention like this. That gets your attention. And if we look here, oh, carbon and hydrogen. Ooh, 2 lines between 2 carbons, that's a double bond. I'm not asking you to know the names of them, but you should be able to identify functional groups. And Dr. White did a lot of research when I worked in the chemical industry with double bonds. Ooh, oxygen with a hydrogen on a carbon, and this is a functional group. And that's called an alcohol, and I work with those. And finally, ooh, not one, but 2 oxygens attached to this carbon, and that's another functional group called the carboxylic acid, which I also worked with heavily at one company. We made them millions of pounds a week. You should know how to do this. All right, when it comes to organic molecules, you should know how to draw condensed structures. I'm not going to go over, I really didn't cover that much, condensed structures with parentheses, but you should know how to put into hydrogen. Remember, there's 4 bonds to carbon. And if they're not there, you put in hydrogens. And when I go through later today, the problem set for organic molecules, I'll practice that with you. Same thing with how to draw cyclic organic molecules. And the key rule is every bend in a line is a carbon atom. And I won't do it that much in this class, but each end of a line is a carbon atom, and each intersection is a carbon atoms. And when you use the line method for rings, you don't show the hydrogen atoms. Now, I asked you to learn 2 general reactions. One is if you take a saturated hydrocarbon, react it with oxygen, you'll get carbon dioxide, water plus heat. That's what happens when you burn something. And that heat is energy, and that happens in your car engine. Now, another one I asked you to learn was hydrogenation of an alkene. An alkene is a double bond. And here you take a double bond, another way of writing that, react it with hydrogen gas, H2, and a catalyst. Catalyst is something that makes the reaction go quicker. And for this reaction, it can be platinum, palladium, or nickel. And you break the pi bond. There are 2 bonds in a double bond. And each carbon of the double bond gets a hydrogen. And my first research project in industry was working with a triple bond between carbon and nitrogen, doing this kind of hydrogenation. And later on, because of my knowledge of this at another company, I was able to help improve production of the hydrogenation of certain molecules. Now, when we talk about organic chemistry, because this is areas I've worked in, there's some things you should know. When we talk about fats and oils, which is an industry I worked in, you should know a fat is a triglyceride. That's a special type of molecule that is a solid or semi-solid at room temperature. Now, you don't have to know what room temperature is, but in case you were wondering, that's defined as 25 degrees C. You should know an oil is a triglyceride that is a liquid at room temperature, 25 degrees C. Now, since I worked in this area, I taught you beef fat, which I worked at a company that bought it, is called tallow. Pig's fat is called yellow and white grease. And the company I worked at, we would purchase every week about 2 to 3, are you ready for this? Million pounds of tallow and yellow and white grease. You can use them interchangeably. Yellow white grease is about 2 cents a pound less than tallow beef fat. If you're buying 150, 200, 300 million pounds a year, 2 or 3 pennies makes up a lot of money. Now, you should know how soap works. Now, soap, and I'm not going to ask you about it, but it deals with what's called surfactants, which is a shortened version of surface active agents or chemicals. And You should know soap has a structure like this, a nonpolar tail, which is called a hydrocarbon tail, and a polar head. And the most important thing about how soap works is like dissolves like. And you learned earlier when we talked about solutions, that means polar things are soluble in polar things, nonpolar things are soluble in nonpolar things. And if you mix two together, they're not soluble. I like that, not soluble. You're out of here. No. And you should know water is polar and dirt and grease are nonpolar. It even says it on the slide. Know this. And because of that, if you had a piece of dirt on your hand, it's nonpolar. Water won't get it off because that's polar. But the soap molecules, the tail is attracted to dirt. The polar end wants to stay as far away out. This is called the micelle. And a micelle looks like this in real life. And in the center here is our dirt. They cut off a segment to show you what it looks like. Here, right here, are the nonpolar tail, the outside, the polar head. And now water looks at micelles and sees the outer part is polar and says, oh, micelle, I'm polar, you're polar, let's go down the drain together. And they do. And that's how you get your hands clean, your clothes clean, your hair clean, what's left of mine, my beard too, and anything else you clean with soap or special type of soap, as detergents for your laundry. Now, another thing you should know, how does a towel work? Now, a towel is made of cotton, and cotton has alcohols, OH groups, and a towel works by attracting water off you or whatever you're trying to dry onto the towel by hydrogen bonding to water. And that's something you should know. And with that, we're done with the review. I'm going to take about a 5-minute break, and then we'll come back and do the organic chapters problem set. See you in 5. I'm back. Profound, wasn't that? Like you couldn't tell. All right, let's go through the organic practice problems. And one thing I noticed, this is the only one I forgot to change. I apologize. There's some cursive here. I'll read it out. Now, these are things, obviously, by now you know why I call them practice problems. Hint, why I call them practice problems. Double hint. And let's go through it. What is a hydrocarbon molecule? It's a molecule with only carbon and hydrogen atoms. Excuse me. And what is a saturated hydrocarbon? It's a molecule with only carbon, hydrogen atoms and only carbon-carbon single bonds. You can use abbreviation like I did. Next, what is an unsaturated hydrocarbon molecule? And that is a molecule with only carbon and hydrogen atoms and at least one carbon-carbon double bond. That's what that is. And a carbon-carbon triple bond. Now, you should know there's four bonds to carbon. 1, 2, 3, 4. Don't count my thumb. All right, four bonds to carbon. Now, you should know how to draw in hydrogen atoms for the following molecules. Now, let's look at, I have 1, 2, 3, this molecule. How do you draw in the hydrogens? There's always 4 bonds to carbon. And if they're not, you use hydrogens to get it up to 4. This carbon has 1 line to it, 1 bond. There should be 4. 4 minus 1 equals 3. So we add 3 hydrogens. This carbon has 1, 2. Well, it already has 2 bonds, but there should be 4 bonds to carbon. 4 minus 2, isn't the math hard? Is 2. So I'll put in 2 hydrogens. Same here, same here, same here. And this last carbon has 1 bond. There should be 4. 4 minus 1 is 3. And that's how you do it. Let's look at C. And the question is for this one, this was C, draw in the hydrogens. So let's remember there's always 4 bonds to carbon. If there's not, you add hydrogens to get it up to 4. Now this carbon, this, and this one all have 1 bond to it already. Well, 4 bonds to carbon minus 1 mean there should be 3 hydrogens. And if we look at this carbon right here, it also has 1 bond to it. There should be 4 bonds to carbon, and that's what you get. Now, let's look at this carbon and this carbon. They both have 1, 2 bonds to it. Well, there should be 4 bonds to carbon, but we only have 2. 4 minus 2 is 2. So each of these will get 2 hydrogens. I forgot to mention this one has 1 bond 4 minus 1, 3 hydrogens. And the last carbon we have to go is this one right here. There's 1, 2, 3 bonds. There should always be 4 bonds to carbon. 4 minus 3 equals 1. So we show that by 1 hydrogen. And that's, oh, we got one more. I almost forgot. Sorry. Let me clean up this. And we have one more carbon. Dr. White almost forgot. That's this one. How many hydrogens is that, right? Or do we need to add hydrogen? Well, there's 1 bond, 2, 3, 4. There should always be 4 bonds to carbon. 4 minus 4 equals 0. So that's right. You don't have to put any hydrogens. And that's how you do this. And that's a skill. Hint. Oh, I'm going for the Guinness Book of Records. You should know how to do. All right, next, how many carbon atoms are in the following molecules? Well, you count C, carbon atoms, in A. And there's 1, 2, 3, 4, 5, 6. Oh, I got it right. Hey, I better. Anyways, let's look at B. And I'm going to write this on my whiteboard so you can see how to do this. Oop, wrong thing. And the question is, I could have put 3 points or 2 points each. And how do you do that? How many carbon atoms are in this molecule? Well, the ones where you can see C, carbon, 1, 2, 3, 4 up here, and this is 5, this is 6, so I can see 6 carbon atoms. But wait, we have a ring. Every bend in a line is a carbon. So 1, oops, I didn't want to do that. 1, 2, 3, 4, 5, 6. 6 plus 6 equal 12 carbon atoms in this molecule. Remember, every bend in a line in a ring is a carbon. Oh, let's try another one. Let's look at C. How many carbon atoms are in here? And I'll do it on the whiteboard. And let me peek back at the structure. And the question is, how many carbon atoms are in this molecule? Let's call it molecule and for problem B, or part B. Count the carbons, C. 1, 2, 3, 4, 5, not the hydrogens. All right, so I have 5 carbons I can see. Wait, I have a ring. How many carbons in the ring? Well, this is an oxygen. I don't count that, but one, every bend in a line is a carbon, two, three, four, five. And that's five carbons. And five plus five, hopefully I got it right, means there's 10 carbons in that molecule. And if we look at D, even though there are double bonds there, that's with the two lines, you count bends in a line. 1, 2, 3, 4, 5, 6. This is molecule is called benzene and it has 6 carbons. Now the last one, E, we have 1, 2, don't count the oxygens, the O, 3, 4 carbons. Now the next thing you should know how to do is determine where are the functional groups in a molecule. Hold on while I pour some more water in my cup. I'm ready to go. And now how do you do that? You look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like this. Hopefully that got your attention. And here, whoa, an oxygen. Bond to carbons, that's called an ether, but you don't have to know the names. I do. You circle it. Ooh, carbon double bond to oxygen with hydrogen and carbon. You circle that. It's called an aldehyde. Oh, look. Well, carbons like benzyl lines are not, but an oxygen with a hydrogen and a carbon, yep, that's an alcohol. And here, the nitrogen with the carbons I circle, that's called a quaternary ammonium salt, which I have patents in. And this is called an amide. The oxygen, nitrogen, give it away. And same with these. Now, in 8, I asked you, give the reaction product or products for the following reaction. How do you do that? There are two reactions, general reactions you need to memorize. Ooh, that's one I've never used before, memorize. I don't think I'll use it again. But anyways, you have this reaction, propane reacting with oxygen. What do you get? Well, that's a saturated hydrocarbon, I abbreviate it, plus oxygen always gives you carbon dioxide and water. And guess what you get? Carbon dioxide and water. Here's another saturated hydrocarbon. Remember, only carbon-carbon single bonds. Oxygen, that also will give you carbon dioxide and water. Oh, I forgot to do one. Let's do this one. And the question is, what are the product or products? And here, what do we have? Well, it's a ring. It only has carbon-carbon single bonds. Remember, there's a carbon here and here, and one line is a single bond. And this is a saturated hydrocarbon. It's cyclic. And when you react it with oxygen, you know what you're going to get because you memorize this, carbon dioxide plus water. And what am I going to get here? The answer is CO2, carbon dioxide, H2O, water. Now, let's look at D. We're reacting this molecule with hydrogen, H2, Ni is nickel catalyst. Look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen for this reaction, carbon-carbon single bond should get your attention, a double bond. When you react a double bond with hydrogen and catalyst, nickel, platinum, or palladium, you break the pi bond, one of those bonds, and each carbon of the double bond gets a hydrogen. However, the rest of the carbons come along for the ride. And I have 4 carbons, I end up with 4 carbons. I broke the pi bond, and each carbon gets a hydrogen, and you put in the rest because there's 4 bonds to carbon. And here again an E, same thing. Only thing that changes is the double bond becomes a single bond, and each of those carbons gets another hydrogen. And same thing in F. Double bond, you break one of those bonds, everything else stays the same, comes along for the ride, and each carbon gets a hydrogen. Now, a couple definitions you should know. What is tallow? Beef fat. What is yellow grease? Pig's fat. Those are all things I work with. I forgot to mention yellow grease, white grease, and tallow are very important chemicals used by the chemical industry to make things like your soap. And if you don't know where to look, every Friday in the Wall Street Journal, they list a weekly price of tallow, yellow grease, and white grease. Now, you should know, how does soap work? And notice I give a hint, give the structure of soap, and talk about micelle. Soap, nonpolar tail, polar head. Water, polar. Dirt, nonpolar. The most important thing, how does soap work, is like dissolves like. And if we're in a room at COD, I'm writing this on a whiteboard showing you this, the like dissolves like, I would write like this. Real big. You should know the most important thing of how soap works is like dissolves like. And remember, water is polar, dirt is nonpolar. And you have your little piece of dirt here on your hand or wherever, on your clothes. How do you get it off? Water will not want to do anything with dirt because dirt is polar, nonpolar, water is polar, and like dissolves like. But soap has a nonpolar tail, which is attracted to dirt because of like dissolve like, but the polar head stays all the way away in the outside, and that forms around the dirt. The whole thing is called now a micelle, and you should know that. And a micelle looks polar. Water sees micelle as polar, and the water says to the micelle, I'm polar, you're polar. I know like dissolves like. I hope you do too. Let's go down the drain together. And it does. It comes off your hand, the micelle. And so when you wash your hands and you rinse them with water, you're getting the micelles, which takes the dirt off your hand. Now, finally, how does a towel work? How does a towel absorb water? And that is by hydrogen bonding to water. And you should know that. And let's do 2 more. And the question would be, all right, I could even make it 4 points each. And how do you do this? Let's call this A. You look at the molecule, you see there's only carbon and hydrogens in the molecule, and it's only carbon-carbon single bonds. It's a saturated hydrocarbon. Let's try this again. My brain stopped spelling. I was always the first one down in the spelling bee. That's better. And this general reaction gives us what's going to happen. Saturated hydrocarbon, you should know, reacting with oxygen, combustion gives you carbon dioxide plus water. Remember, organic chemists do not, unless we have to, and for my test, you do not have to, for these type of problem, balance the equation. So what do you get? Carbon dioxide and water. Let's do one more. And the question is, what are the product or products you get in B? And look for what's different. What's not carbon, what's not hydrogen. For this one, what's not a carbon-carbon single bond, ooh, a double bond, should get your attention like that. Hopefully that did. And you should know the general reaction for my class, double bond, reacting with hydrogen gas, H2. This is a catalyst. And the catalyst, I'm abbreviating CAT period, can be nickel, Ni, platinum, or palladium. And this has a pi bond, which I'll never ask on a test, and a sigma, and you break the pi bond, and each carbon of the double bond gets a hydrogen. And do you break for these, except for combustion, like I did up here, A, you don't break carbon-carbon single bonds. So you have 1, 2, 3, 4, 5 carbons. You better end up with 5 carbons. 1, 2, 3, 4, 5. The 2 carbons of the double bond only have 1 bond between them, and each one gets a hydrogen, just like the general reaction here. And now I know there are 4 bonds to carbon, and I can put in the rest of the hydrogens. And that's how you do it. And with that, I'm done. But first, don't run away yet. Well, actually, you're watching this, so I don't think you're going to run away, but don't close the video yet. All right. Monday after lecture, I will be giving test number 4. Monday is the deadline by the end of the day for the extra credit project if you want to do it. It's optional, but it's like being able to get 10 more points to your test or your final total, which could make the difference between an A and a B, C and a D, or D and F. Do it. Before you do it, send it to me, email, and I'll check and let you know what's wrong. And then you can get 10 points. Now, next week's going to be very important. Why? Because I am going to do a review for the whole semester. I will go through each hourly exam review, and do some practice problems too with you. And that will help you on my final. By Monday, I will have and send out an email posted in Blackboard, information about the final exam. A week from next Monday, during finals week, I will give the final exam. You'll have from Monday morning, there'll be no lecture, 9 a.m. or maybe even earlier, until Tuesday, sometime afternoon, and maybe I'll make it 2 or 3 p.m. to take my final and upload it to Blackboard. And also, one last announcement. Monday, I'll have a very special surprise if you come to lecture. I will be talking about a chemical plant. You'll want to come. It will be awesome. But I will cut it out of the video. I'm not going to post it on another video. So you'll have to come Monday to lecture to see this really cool thing. And with that, I'll say, don't forget, I have my office hour tonight from 6 to 7:15 on Zoom. And if you don't come tonight, have a good rest of the weekend. Study for test number 4, which is next Monday. And with that, I'll say, Gang gesund. Goodbye.